So there are a lot of reasons why we want to use virtual memory, and from chapter 15, we're going to actually start with realizing or implementing virtual memory. How would we actually use virtual memory? So chapter 15.1 is some assumptions that you can read. I'm not going to go through them right now. I'm just going to go through them whenever we need to use these assumptions. So we will start with 15.2. Um, so we start with an example of, virtual memory. So we want to implement address translation, and we're going to understand that um, using a simple example. So we're going to be looking at 15.1. This figure is central to chapter 15.2. So what the code uh, will look like in C is we have a void function, and integer x is 3000, x is x plus 3. So this is the code that we want to implement. The assembly looks like this. Once we compile into assembly, we have these virtual address spaces 128, 132, 135. So we can see that this is a pointer. EBX is a pointer. So it holds the value of the memory, and this holds the actual value. This register holds the actual value, and 132 adds. So basically, what this part is saying is, let's say we have the CPU here, and then we have the EAX register and the EBX register. So the difference between the EAX register and the EBX register is, we're going to see it soon. So first, the CPU will have the program counter register. The program counter will look at 128 first. It's gonna see, okay, we have EBX, and the EBX is going to have the value 15K, which is 15 times to the 10, which is 1024. The EBX is gonna have this value 15K, which is right here. And basically what this line does is it just adds a 0 to the 15K, which is 15K, and gets the value, moves it to EAX. So EAX is gonna be 3000 now. Okay, so instruction 128 is done. Next instruction, the program counter will add +4 to move to 132. 132 is going to add 3 to the EAX. So EAX is going to be 3. Good. And then we're going to this time move the value of EAX to the dereferenced EBX. So EBX is 15K. It's still 15K here. So, and EAX is 3003. So now we are going to, this is going to have the value 3003. Basically in assembly, the way things work is like the variable in C code, we have things like variable X, int variable X, but in assembly there's no such thing. It's just the address. That address stands for X. So when we turn C code to assembly, this is just 15 times 2 to the power of 10, just something like this. That's just the concept of variable doesn't really variable naming doesn't really exist. It's just the memory. And this would stand for X if it were C code. So that's kind of how it works. So that's what the book is saying at this point. And then it's saying, okay, from the program's perspective, its address space starts at address 0 and grows to a maximum of 16K. So that is 16 times 10 to the 2 to the 10, which is probably 16,000 something something, right? Right. 6, 2, 1, 2, 4, 6, 2, 4, 2, 4, 8, 3. I don't know if I'm right, but it's gonna be something like this. This is gonna be the address. So the address is 0 to 16384. I might be wrong. I don't know. All memory references it generates should be within these bounds. However, to virtualize memory, the OS wants to place the process somewhere else in physical memory, not necessarily at address 0. So we just looked at how a simple 3 instructions work. And then, so what we want to do is we want to relocate this process in memory in a way that is transparent to the process. How can we provide the illusion of a virtual address starting at 0, and in reality the address space is located at some other physical address? An example of what physical memory might look like once this process's address space has been placed in memory is found in figure 15.2. Oh, I'm sorry, it's right here. 15.2. Let me erase this one. So this is what we want. So previously we had this looking like this, but now we want this looking like it starts from 32K to 48K. So this would be 32 times the address will be here, and then it must end at this address here. So that's what's saying it's relocated process. So it's saying like the process is the memory is saved in chunks of process. So the process is relocated, meaning that it's relocated from, let's say, 0 to 16K, which is what it thought it would be in, but in fact it's 32K to 48K. So it's a relocated process here. We use the term relocated often. Relocated is used very often actually to kind of just refer to this concept of this. And then you can see that the other slots are free, but this is, we don't really care. You don't really have to care about this part, because the operating system is what determines, this operating system sitting at the top of the memory is what determines what chunk of the memory is going to be in use and what it's not going to be in use. So you can see that it uses the term allocated. So this memory is allocated for this allocated memory is used for as a relocated process, right? That's kind of how you think about it, because the process actually thinks of itself as this. The code in the process is just written as this. Right. So 15.3 is where we actually talk about the relocation. So this part talks about the most basic, the start of of virtual memory, relocating memory, which is base and bounds. Okay, base and bounds also called dynamic relocation. We're going to see why it's called dynamic relocation later, but honestly, this is just the opposite of static relocation. Um, and you'll see why. I mean, it's not hard. The term dynamic is intimidating, but it's not hard. So the base register is. I think I prepared a yeah, I prepared a picture for you. So here is the program, the process. Here's the memory, and then memory relocated process A, relocated process B, and relocated process C. And then here's the base register that the OS, the hardware has. The base register points to the start of the relocated process B. The limit register points to the end of the relocated process B. So what it's saying is saying the OS can control the memory, the actual physical memory that it's going to relocate to, right? So bounds is also called a limit. That's why in so that's why in my example from CSL lab we use limit instead. Um, okay. Okay. So that's that, and oh yeah, let's talk about static relocation, which is called software-based relocation. Now, hardware-based is where we use base registers and base register, right? So base registers are like, this is within the CPU. It's a register, right? So it's hardware-based. So before hardware support, some software systems performed um, relocation purely by software. So purely by software means back to the software tool. It means it didn't use an address space starting from zero. If if we were to say it will start from 16K, right? Everything here would be added by 16 and then compiled, right? So the loader takes an executable that is about to be run and rewrites its addresses to the desired offset in physical memory. If an instruction was a load from address 1000 into a register, so this means address 1000 move to register EAX. The value of 1000 and the address space of the program was loaded starting at address 3000 and not 0. The loader would rewrite the instruction to offset each address by 3000, like this. In this way, a simple static relocation of the process's address space is achieved. But this has numerous problems. Also, the reason why we are learning hardware based relocation. First and most importantly, it does not provide protection. Processes can generate bad addresses and thus illegally access other processes or even OS memory. Hardware support is needed for true protection. Another negative is that once placed, it is difficult to later relocate an address space to another location. So static relocation is also it could also be a form of virtualizing memory. Honestly, because the program, when it compiles, it thinks um, it has addresses from zero, but then the loader changes the instruction to the offset. The problem with this is that, you know, is protection. But then naturally another question is, well then, can't the loader have a mechanism where it says, okay, you cannot go past this bound, basically set a bound for itself. Can't the loader do that? But one thing that I think is, does the loader know what the bound should be? Right? As um, for hardware-based relocation, the CPU has the bound register, the limit register, right? Whatever you call it, it has the bound register, and it sets the bound register because the kernel has the control over the memory to be used. But the loader is not a in control by the kernel, if you think about it, right? But the actual problem with this is that what happens after the loader does static relocation. After the loader doing static relocation using like base registers and let's say um, all that, we must be aware. Okay, even though there is no problem with the thing, with the addresses, and they're all within the bounds after the static relocation. The problem is we need the process is going to run stuff. Then they can easily just say, okay, the next instruction is um, let's say 15K plus 3K, which is 18K. It is over the bound. Let's say the process just makes an instruction that just goes over the bound. Let's say the bound is 32K. They make a 35K, and then they just say, okay, use this 35K, um, get the memory from it, right? And then we have nothing, because bear in mind we don't have the base and bounds hardware relocation, where the hardware checks for the bounds. So this is why there must be a bounds checking by the hardware for each instruction run at runtime. At runtime, the hardware constantly checks. Okay, well, is this address within the bounds? Right? Is this address after the base and with under the bound? You understand? So with static relocation, that kind of protection isn't available because the process runs after the loader, right? But the hardware controls the runtime. It sees the very final output, the very final things that the addresses that the process is trying to approach. It sees that it's at the very final gate. So and it checks, okay, is it before, after the base, before the bound, before the limit? It checks that. So it does provide 100% protection. Hardware support is needed for true protection. So well then, if we have to check whether the memory is between base and bound anyway, we would likely just so use base and bounds. And then also, then some could say, well, we can use static relocation and then use hardware support as well with base and bounds. Well, okay. It does get kind of messy because you can just with if you just use hardware support, you just do virtual address plus base and then check whether it is between base and bounds. It's very simple, very easy, very neat. But some could say, just do the static plus base at static relocation and do check base and bounds after with hardware. And well, it is likely that you can do that, but um, that is error prone. Using static relocation itself is, if you actually start implementing it, like it's very dirty and very messy. Using hardware relocation is just neat. It's just two things: as add and then check. But when you do static relocation, just gets in just so many messy cases. But let's say we just ignore that and then just use that, right? And just use that. The next problem we have is movability. So what we have to do is we have to relocate an address space to another location in order to implement the memory technologies that we are going to talk about later, um, like swapping, demand paging, and all the memory management techniques that will come later. We need to be able to do relocation um, as we want to do it. Like let's say the memory was in 16K, but then we want to move that process to 32K. We need to do this kind of stuff. But for static relocation, it's the physical address translation. The result of address translation is baked into the process, and then it's just gonna be using that, right? If you want to say, well, you know, why don't we just for relocation just use hardware at that case? Well, then why don't we just use hardware for the whole thing? Like, so I mean, this is like I spent a lot of time talking about this, but software-based relocation, and if you like really think deep about this, there's a lot of problems. There are a lot of problems um, that make you really shift toward hardware-based relocation or dynamic relocation. Okay, today I think I'm just gonna do until 15.3. I spent way too much time on this part. So where were we? Yeah, we were talking about relocation, Each program is written and compiled as address 0, just like the thing we saw before. This one. However, when a program starts running, the OS decides where in physical memory should be loaded. To be more exact, the OS decides where in physical memory it should be loaded before the program starts running. Right before. So it's kind of, to be more exact, this right before. Say, play with words, but yeah. And sets the base register to that value. So here the important thing is the base register is the core of address translation in dynamic relocation. And then, so when the process is running, any memory reference, this is important, any memory reference translated to the physical address by adding the base. Okay. So each memory reference generated by the process is a virtual address, and then the hardware turns it into a physical address. To understand this better, let's trace through what happens when a single instruction is executed. So from our instruction earlier in the sequence, what this does is in EBX we had 15K, which is the memory that stands for X, the variable integer X, in C concepts. And then it moves it to the EAX, which is the value of the memory 15K was 3000. So this will be the result, right? The program counter is set to 128. So the PC of the CPU needs 128. When the hardware needs to fetch this instruction, it first adds the value to the base register value 32 KB to get a physical address. Okay, so in the memory, there's the code, right? So let's say the base register was set to 32K. And then the top part allocated for this process has the instruction 128. When in fact the address for 128, so there must have been, let's say, a instruction that says fetch from 128 within this process, within this program. Then when the PC fetches it during this fetching process, at the middle we add 32 KB, 32K, and then we get 32896, which is the actual address 32896, and then it fetches it. Next, the processor begins executing the instruction. At some point, the process then issues so when it's set to 128, PC is set to 128. When it fetches, it turns to 3. There must be something that does the calculation 3288, 32896, and then goes here. At some point, the process then issues the load from virtual address 15KB. So here is 15K in the EBX. adds 32K, getting 47K. So EVX has 15K. The processor does the load. During the load, goes through some hardware, adds 32K, and then gets the actual stuff. This is what we refer to as address translation. It's called dynamic relocation because this happens at runtime, unlike static relocation, which happens not does not happen at runtime, happens before the runtime. And also we have movability. Now you might be asking, the bounds register. Now bounds is used for protection within bounds. So base and bounds registers are hardware structures kept on the chip. The memory management unit, also called the memory management unit. So right now our concept of the MMU is just base register and bound register. Bound registers can be defined in two ways: size of the address space, physical address of the end of the address space. We usually assume the former method so the bound registers can hold the size or the physical address, but we normally choose the size. Finally, let's look at example translations. So let's imagine a process with an address space of size 4K, loaded at physical address 16K. So we can see 16K to 20K. So 0, 16K, 1K, 17K, 3000, this, 3000 plus 16K, gonna be this. This plus 16K is gonna be bigger than 20K, so it's gonna be out of bounds. So let's actually do the calculation for the final one. So 16 times this, I think we calculated this previously. Maybe I erased it. I think I erased it. It's what, 16,384, and we add 4,400 to this. We get this, and 20K is 20 times this, which is 20,480. It is indeed smaller than the physical address we tried to get, so it's out of bounds. Okay, let's do the hardware based dynamic relocation summary in the next tutorial. And then we're going to talk about operating system issues. And then the whole summary for this chapter. So in the whole summary for this chapter, I might be talking about the introduction here, and also the assumptions maybe. I don't know.